So in the second sections, we have a couple of talks that they will mainly focus on stochastic background. The first talk that we have is by Mark Hindermarsh, that will talk about characterizing the gravitational wave power spectrum from early universe phase transition. So whenever you're ready, Mark, please feel free to share your screen and start your talk.
Thanks very much. And hopefully I can be seen and heard, or rather the screen.
Everything seems perfect.
Yeah, good, thanks. Well, I'm sorry that I can't be in Glasgow right now. Anyway, this is the next best thing. So I'm talking about a particular aspect of Lisa's ability to probe physics of the early universe, which is a phase transition at the electroweak scale. So first of all, I'll start by talking about phase transitions in the early universe. And we know that in the standard model, the state of matter in the universe changes its character, going backwards in time at about a millisecond after the beginning. We have the quark-hadron transition, where quarks become bound into hadrons, and then earlier at about 10 picoseconds, we talk about the electroweak transition, where the masses of elementary particles were generated by the Higgs field switching on. And even earlier than that time, well, we don't have any direct idea of what might be happening, and there are perhaps new interactions and new symmetries which might undergo similar transitions. Now, the interest is that if a transition like this happened as a first order phase transition, and in order to fix your mind, water undergoes a first order phase transition when it goes between the liquid and the vapor state. And this is actually very close to the kind of phase transition that we're thinking about. And as you know, that when you boil or boil water or condense vapor, you get departures from equilibrium and homogeneity. Departures from thermal equilibrium can result in the generation of a baryon asymmetry, which is one reason for being very interested in first order transitions to the early universe. And the departure from homogeneity in the universe can lead to gravitational wave production. So, so how does the transition proceed? Well, it proceeds by the nucleations of small bubbles of the low temperature stable phase just below the critical temperature, where the new phase becomes stable. And these bubbles expand, they generate pressure waves in the hot fluid, and essentially produce something like a fizz in the early universe, which produces gravitational waves. And the gravitational wave spectrum has information about the physical parameters of the phase transition. What you see in the video is a numerical simulation of a relativistic fluid undergoing a phase transition. The sort of the hot areas are areas of high kinetic energy in the fluid's moving around, and the blue areas are stationary fluid. And what these moving bands are is in fact sound waves. So that would be very interesting if it happened in the universe, and we'll explore the consequences. But before we do, we have to confess that in the standard model, actually the transition, the mass generation transition, the electroweak transition, is a crossover. What that means is it's like the liquid vapor transition above the critical point. So what happens is something like the system moves smoothly from a dense vapor to a not very dense liquid. So there's no departure from equilibrium, and no generation of gravitational waves. What that means is that the search for gravitational waves from an electroweak transition is in fact a search for new physics that we know is needed because we need an explanation for the baryon asymmetry of the universe, and also other shortcomings of the standard model are known, like no explanation for dark matter. So what frequencies could we expect gravitational waves from an electroweak scale phase transition to be generated, assuming we accept that some new physics might be around at or just beyond the electroweak scale? Well, you can work out just by looking at what the Hubble time is redshifted to today, that the lowest possible frequency is about 10 microhertz. And any causal processes happening at that scale must be happening at a higher frequency. And that just so happens to, at least for the first few decades, to coincide with the sensitivity of space-based interferometers like LISA. And so we've seen this before. Nikos showed this nice picture to us this morning, and I just thought I'd add on to it what a little cartoon of what a phase transition signal might look like, in at least one that peaks at a few millihertz. So, the exciting thing is that LISA might be able to observe such a signal, and so we would like to be able to characterize the signal and also understand what information LISA might be able to extract from it. And so let's go into a little bit more detail about the gravitational waves from a phase transition. So in the phase transition, there are some thermodynamic parameters that are particularly important for generating, for calculation of the generation of gravitational waves. So first of all, one of the most important things is what temperature does the transition happen? What temperatures do all the bubbles which make the transition nucleate, the nucleation temperature? Then how much energy is released? So that's we parameterize that by the strength parameter, which is essentially you can think of as the latent heat divided by the total thermal energy or at the nucleation temperature. Then there's the transition rate, which is essentially the time it takes for the transition to complete. So if we look at the transition, if we look at the fraction of the universe that's in the metastable phase, the universe, as time goes on, the universe reaches the critical temperature. It's cooling down here, reaches the critical temperature, and then starts to supercool. And then a few bubbles nucleate from the thermal fluctuations, and then more and more, and the transition happens ultimately very quickly. And so this is a different time scale from the time at which either the nucleation happens, which is typically shortly after the time at which the critical temperature is released. So that's an important time scale, which is always turned into a rate. The wall speed, the speed at which bubbles expand, which is they quickly reach a terminal velocity due to friction with the surrounding fluid, and also the sound speeds in the fluids, both in the two phases, and finally the effective number of relativistic degrees of freedom in the plasma. That's actually not a very important parameter, but it should be there. And then on the other side, we want to know what the shape of the power spectrum is. What's the peak amplitude, the peak frequency, and any other shape parameters with which we can describe the transition. So building on numerical simulations, we can describe the transition using what's called the sound shell model. So we assume that the velocity field is just a linear superposition of all the velocity fields set in surrounding the expanding bubbles, and then we just add them up, basically weighted by the size of the bubble. And ultimately, there are two length scales which set the length scales of the gravitational waves, which are the mean spacing of the bubbles, which make the phase transition, and the width here of the pressure shell surrounding the sound shell surrounding the bubble. And in this model, one finds that typically there's a double broken power law, a sharp rise to the first scale, the bubble separation scale, or its inverse if you're talking about wave number, and then some kind of structure around the peak up to the inverse sound shell width, and then a power law decay, which at high wave number becomes k to the -3. So okay, yes, I think that's enough. So one can compare the predictions with numerical simulation, large-scale numerical simulations, and they work quite well for transitions which don't release very much in the way of energy. So when the linearity assumption is very good. So this is this alpha energy release parameter. This model is actually encapsulated in a Python package, which is real soon now, ready for public release. But certainly it has a kind of at the moment limited domain of applicability because of this linearized approximation, which is with some phenomenological corrections from numerical simulations. But it's regard this as a start towards a more complete predictive package. So what do the power spectra look like? So here's what they look like as compared to LISA sensitivity and various foregrounds you might expect, such as confusion noise from compact binaries, from galactic compact binaries, and also extragalactic ones, binary black holes, basically. And what's shown here is what happens when you vary these various thermodynamic parameters, phase transition parameters. So the wall speed, that actually is perhaps the most interesting one, because that changes the shape of the power spectrum the most. The transition temperature is the simplest one. All it does is change the peak frequency without changing the shape. The transitions strength, so the amount of energy released, mostly just increases or decreases the amplitude of the gravitational wave power spectrum. It does have small effects on the shape. And the mean bubble separation, the bigger the bubbles, the stronger the signal, but also the lower the frequency. So you can see that in principle there is information about these four parameters and possibly more in the gravitational wave power spectrum. So perhaps we can hope to infer something about them. So what sort of signal to noise ratios can we expect for some of these transitions? So here's just some examples. So a temperature that's around more or less exactly the electroweak scale, the temperature somewhere between the mass of the W and Z bosons and the Higgs boson. So, and wall speed somewhere between 0.4 and 0.9 of the speed of light. One expects relativistic wall speeds because it's a relativistic fluid. And so this is the strength parameter. So with strengths greater than 0.1 or 0.2, you expect reasonably high signal to noise ratios, providing the bubbles are rather large compared with the not large compared with, but getting towards the Hubble radius. So this is the worst case scenario where the confusion noise is is not removed at all, but there is some hope that the confusion noise from galactic binaries can be removed because of its annual variation, in which case this is what the signal to noise ratios are. So that's without the galactic binary foreground. So, so what can we hope to see in terms of the parameters? So one can, as a preliminary guess, we looked at the or preliminary analysis. We used Fisher matrix to see what could be observed for various wall speeds and transition strengths. And it turns out that the best constrained parameter is actually the wall speed, and that's because of this shape effect. So that's something for the theorists calculating from underlying theories to take away. So we're not the only people to think about this. Others have looked for searching directly for this approximation to the phase transition signal, this double broken power law, and others have been looking for various spectral shapes of how easy it is to determine the parameters of cosmological gravitational wave backgrounds in terms of in the presence of foregrounds that we know about. And currently in progress, we're looking at that in more detail to pin down more precisely what peak amplitudes and frequencies can be detected in the presence of realistic foregrounds and noise. And also then how you might determine, go back to the thermodynamic parameters such as latent heat or wall speed, knowing this parameterized double broken power law. So in future, of course, we need to understand the non-linear evolution, so abandon this linearity assumption, which is a challenging issue. We need to look at the vortical turbulence, also shocks, and in terms of and to understand better the equations of state and the effect of the different sound speeds. So we've got a couple of talks. Well, it's a on the question of turbulence. We've got a couple of talks. There's a pre-recorded talk by Pierre Leclerc, which I recommend you look at. And after me, Alberto Ropopo is going to talk about turbulent magnetohydrodynamic turbulence and generation of gravitational waves. So to conclude, LISA. Well, I hope I've convinced you that LISA will probe the physics of the electroweak transition, and there is some ability to measure or constrain at least phase transition parameters, and the one that's likely to be best determined is the wall speed, the expansion speed of the bubbles. And actually that's interesting because that's the hardest one parameter to calculate because it's a non-equilibrium calculation. So we need to extend the domain of applicability of our current toolbox for calculating gravitational wave spectra. And if we can perhaps make gravitational waves as good a probe of the electroweak era. There's as much information in the gravitational wave power spectrum as there is in the CMB from the decoupling era. So thank you very much.
Thank you, Mark. All right. Is there any question for Mark? I don't see any hands up. Please raise your hands or just drop your question in the chat. In the meantime, since there is no questions, I will just make one for Mark. This is a question that is recurrent usually whenever there is a talk regarding stochastic background from say the early universe or laser, and the answer is evolving in time, let's say, each time that I see an answer for this question. The question is, how can you distinguish a stochastic background from a real universe from a possible astrophysical stochastic background that can superimpose, let's say, to the same signal and in the same frequency band?
Yeah, it's really that it's really about the shape of the spectrum, so that there really is a lot of information. I mean, in LISA data after 4 years, so there's hundreds of thousands of frequency bands, and so you can really distinguish between let's come back and sort of abandon sharing. You can really distinguish between actually, I'm not sure what I'm sharing now. Sorry.
We were seeing your desktop.
Let's try again. Yeah, that's better. So you can really tell the difference between this between these shapes, even if there's three a signal which is composed of a sum. So this is if I show this slide again, which I skipped over. This is actually a Monte Carlo with these over the phase transition parameters in the presence of foregrounds. So it's really about the shape, and of course, as I mentioned it, with the galactic binaries, there is the annual modulation, which is not included in this Monte Carlo.
All right, thank you. We have just time for another question. Please go ahead. Thank one.
Hi, Mark. May I ask a simple question? Could you give some comments? Is the LISA more sensitive to bubble velocity or the phase transition temperature? I mean, is it a universal result that the bubble velocity is most sensitive for LISA detection?
Yeah, that's a good question.
I mean, for different the power you choose, double power, single power, is for use Fisher or MCMC, is the result universal?
Yeah, yes, we have. We're just in the process of finishing a paper where we can check that the Fisher and MCMC give similar results about uncertainties. But in answer to your question, that there are degeneracies. Basically, changing the temperature changes the peak frequency. You might think that's very well determined, but several other things change the peak frequency as well. I mean, in particular, the mean bubble separation also changes the peak frequency, so there's a strong degeneracy there. And although the mean bubble separation does change the amplitude, so does the latent heat. So there's actually a complicated three-way degeneracy, but the thing with the wall speed is that it really changes the shape quite a lot. So that's why it's most sensitive to the wall speed.
Okay, we have one last question in the chat, which I'm going to read out loud. Thinking even beyond LISA, what will be required to increase the odds of discovering a gravitational wave background from phase transitions? Going to lower frequencies or better sensitivity, or both?
Yeah, so given that if we're thinking about phase transition at the electroweak scale, I think it would be probably going to higher frequencies would be because that under the sort of the presumption that there's more physics at the TeV scale, which is a higher, corresponds to higher frequencies. So going to so it's actually both going to higher frequencies and higher sensitivity, which is somewhat challenging.
All right, that's great. So let's thank Mark again, and let's move to the next speaker, who is Alberto Roper-Paul. I'm going to speak about stochastic gravitational wave background produced by magneto-hydrodynamical turbulence from cosmological phase transition. Please feel free to start whenever you want, Alberto.
Okay, hi, yes, can you hear me now? And you can see my screen, right?
Yes.
Okay. First of all, thank you very much to the organizers for putting this workshop online. It's been very nice, and for giving me the chance to present my work. And also thanks in particular to Nikos Karnesis and recently Mark Harmash to introducing most of the things that I will be talking about stochastic gravitational wave backgrounds, and then the production of these gravitational waves from phase transitions. So I will be presenting some recent results on the production of gravitational waves precisely from MHD turbulence, which Mark Harmash has already introduced for the production of gravitational waves from the phase transition itself and from sound waves and acoustic turbulence, and mentioned that it's also necessary to extend this to the knowledge when we have actually turbulence going on, and also the presence of primordial magnetic fields, which is what I will be covering in this talk. So I will be presenting the results of these 4 papers that I have listed here, which are with some of my main collaborators, with whom I also acknowledge for this work. So I'm gonna go very briefly through the introduction, since most of this has already been talked about by Mark Harmash. So we have we expect to have a cosmological gravitational wave background, which there has been a huge effort within the LISA community, and there's still a lot of work to do in order to disentangle this from astrophysical foregrounds, as well as disentangle the different signals that will be contributing to the gravitational wave backgrounds. And in particular, as Mark Harmash was explaining, if we have a gravitational wave signal produced at the electroweak phase transition, then this we expect it to be probed by LISA. Since we expect it to be peaking around sensitivities of 10⁻⁵ to the millihertz. Similarly, I will very briefly be showing some results that are relevant for the QCD phase transition, since in a similar way, the characteristic temperature at the electroweak phase transition puts the peak of these signals around millihertz. Also, at the QCD phase transition with a energy scale of around 100 megaelectron-volts, this would be peaking around the nanohertz frequencies, and therefore we might able also to probe the signals produced at the QCD phase transition with a pulsar timing array. So we might have many different sources in the early universe, in particular from phase transitions, and we have been conducting numerical simulations in particular to study those from MHD turbulence, which can be, for example, the production of turbulence in the velocity fields directly from first order phase transitions, as Mark Harmash was already talking about, and as well produced from primordial magnetic fields. In general, due to the extremely high conductivity of the early universe, we expect to have a highly coupling between magnetic and velocity fields if they are present in the early universe, and therefore during the first order phase transitions. So we need in general to be performing numerical simulations, since this is an extremely nonlinear system, as I will be presenting. So in general, we might have a contribution from many different sources. So we might have MHD turbulence, but as well bubble collisions, sound waves, cosmic strings, as well as primordial black holes, or even signals from inflation. So it is extremely important to know the spectral shape of these different signals in order to then be able to, once that we have the detection by LISA, to be able to disentangle the different signals and to be able to get information from such signals, and from therefore the production of such signals from MHD turbulence, and what are the sources that are actually producing that. And finally, to extract information on the first order phase transitions, as the thermodynamical parameters that Mark Harmash was talking about in the previous talk. So so we have been focusing on studying in particular those coming from MHD turbulence, and then in the end we'll have a contribution from MHD turbulence as well as sound waves, where the specific amplitudes it's still uncertain, and it's some ongoing work. So I was saying I will be focusing on primordial magnetic fields in this talk, and we expect to have produced or to have present during the phase transition, in particular during the electroweak phase transition, primordial magnetic fields. These are strongly coupled to the primordial plasma, and therefore they inevitably lead to the production of MHD turbulence. And these primordial magnetic fields, they can either be reinforced by the primordial turbulence via dynamo, as well as that they can also lead to the production of MHD turbulence if we have some presence of magnetic fields and the production of turbulence due to the first order phase transition per se. We expect from some astrophysical observations by the Fermi collaboration to have magnetic fields in the larger scales of our universe, and it is very difficult to explain this from astrophysical observations, although there are some efforts in doing so, and it might be one of the scenarios. But we expect these primordial magnetic fields to actually have been generated during cosmological epochs or during phase transitions. So with such observations, we can put some lower bounds on what are the strength and characteristic lengths of the magnetic fields that we expect to have been generated during the first order phase transition. And on the other hand, we also have some upper bounds that are mainly coming from the Big Bang nucleosynthesis. So therefore, we can give some upper and lower limits on what are the strengths of such primordial magnetic fields. And with this, in this limit of upper and lower bounds, we can therefore study what is the production of gravitational waves when we have such primordial magnetic fields produced at the electroweak phase transition. So here is I'm showing that the frequencies at which the different gravitational wave detectors are probing. So in the largest frequencies, as you know, we have the ground-based detectors as the current LIGO, Virgo, and CAGRA collaborations. And in the around the millihertz frequencies, we have the space-based detectors as LISA. And in the around the nanohertz frequencies, we have these are the recently reported potential observations from pulsar timing arrays, which are still not confirmed to be a gravitational wave background, but they are some common process spectrum around that are common to many pulsars. So these might in future be shown to be a gravitational wave background, but it's still not the case. So these would be peaking around nanohertz. So if we have gravitational wave signals that are produced from a phase transition, for example, the one from electroweak phase transition, this is the expected signal that we expect to have from MHD turbulence. And this is based on an analytical model that we have recently developed in this paper and that we have been validating with simulations under a certain range of parameters that I will be explaining about in a moment. And in future, we want to keep studying such types of spectra and with better expectancy spectral shapes for the resulting signal. So as you can see, we have a signal produced at the electroweak phase transition, as I was explaining before. This would be peaking around the millihertz, which is the maximum sensitivity for LISA. If the characteristic length scale of such primordial magnetic fields is around 100 of the Hubble horizon at the time of generation at the electroweak phase transition, and this can also be probed by pulsar timing array if the signal is produced at the XIV phase transition, as we have actually studied in this specific paper. So I'm going to go now through the model that we're using to compute such signals. So we have been conducting direct numerical simulations for which we use the Pencil code, which is an open source code that you can find on GitHub and you can download and use. And we have a big user and contributors community that we have that we are working on this code. In general, for solving sets of partial differential equations, although it's particularly motivated for MHD turbulence. And within this code, we are solving for the relativistic MHD equations, which are adapted for the radiation-dominated era at which we have these phase transitions. And once that we solve for the MHD evolution of the velocity and magnetic fields, we are coupling the solutions to a solver for the gravitational wave equation, as I will be showing in a moment. As I was mentioning before, due to the extremely high conductivity of the universe, we expect to have MHD turbulence, which is which is governed by the MHD equations, which are highly nonlinear, and therefore, in general, we need to perform a numerical simulations in order to study this, and unless we are under some certain range of parameters that for which we were able to develop the analytical model that I was presenting a moment ago, and that I will be in a moment coming back to. So the model that we are solving within the pencil code, on one hand, we have solver for the gravitational wave equation, in which we are assuming an isotropic and homogeneous universe, which is governed by the Friedmann-Lemaitre-Robertson-Walker metric tensor, and on which we have tensor mode perturbations above the background metric. And with for these tensor mode perturbations, we can derive the linearized equation for gravitational waves, in which we have the rescaled strains of the tensor mode perturbations of the metric, which are sourced by the stress energy tensor, which in this case, it is constructed from the velocity and magnetic fields. And after that, we need to take the trace and transverse projection due to the gauge invariance of the tensor mode perturbations. So this is the wave equation that we're solving for the gravitational waves. And the stress energy tensor is described by the velocity of magnetic fields, for which we are solving as I was saying, the set of MHD equations. So we're using an MHD description in order to model the primordial plasma after the electroweak phase transition in this case, for which we are using an ultra-relativistic equation of state, which is appropriate for radiation-dominated era for the pressure, and we're solving the equations above the expanding isotropic and homogeneous universe. So the contributions to the stress energy tensor are coming from the fluid motions, so from the velocity fields, as well as from magnetic fields via the Faraday tensor. And once that we construct the stress energy tensor, which will be sourcing the gravitational waves, we are also able to derive the conservation laws, in which we use co-moving variables for pressure and magnetic field, such that the final set of MHD equations are conformally flat. So they resemble those for a flat non-expanding universe after we have rescaled them with appropriate power loss of the scale factor. So this is the final set of MHD equations that we're solving, which are the conservation of energy density, the conservation of momentum, as well as the induction equation for the production for the dynamical evolution of magnetic fields. And these are the equations that we're then solving within the pencil code. And once that we solve for this dynamical evolution of the velocity of magnetic fields, we're able to construct the stress energy tensor, and finally source that for the production of gravitational waves in order to finally compute the gravitational wave background that is produced due to this MHD turbulence. So now I will give the numerical setup that we're using for these simulations before going finally into the results. So on one hand, we can model different fractional helicity of these magnetic fields. And again, this is also applicable to vortical velocity fields, the results that I will be showing, in which we model, in this case, the magnetic field is initially present and it already has a turbulent spectrum, which follows a Bachelor spectrum at the largest scales, which is expected due to causality and the divergence less of the magnetic fields. And it follows a Kolmogorov spectrum, which is characteristic of turbulence, proportional to k to the minus 5/3. In order to do that, we initialize the magnetic fields with Gaussian random with a Gaussian random field, and which follows this specific spectral shape, which is, as I was saying, the Bachelor spectrum at the smallest wave numbers or largest scales, and k to the minus 5/3 in the smaller scales as a smooth broken power law. So we have some parameters, some free parameters on these initial conditions, which are the strength of these magnetic fields, the fractional helicity of such magnetic fields, as well as the spectral peak, which characterizes the characteristic length of these magnetic fields. And these are actually depend on the thermodynamical parameters of the phase transition or the different magnetogenesis mechanisms that we might consider for the generation of magnetic fields, which I don't have much time to get into. And finally, the specific time at which these gravitational waves are being generated, which is around 100 megaelectron-volt. If we're studying the QCD phase transition, around 100 GeV for the electroweak phase transition, which is relevant for LISA. So these are some some first numerical results that we obtained after we completed these simulations using the pencil code, which actually I presented these preliminary results 4 years ago in LISA Symposium in Chicago for the first time, in which we obtained some novel flat scaling for the spectrum divided by wave numbers. So it's linear in terms of omega. And then the final gravitational wave spectrum is actually proportional to k to the minus 11 thirds for such a magnetic spectrum. This was actually different to what was initially expected from analytical estimates, which were expecting this to be proportional to k to the second power below the spectral peak. And we actually observed in the numerical simulations, this is a plot of the value of this spectrum as a function of the combination of wave number multiplied by time, that it actually becomes flat only after a time, which is an increase of time t minus 1, where 1 is just the normalized initial time. So this is normalized by 1 Hubble time. And this is approximately proportional to 1 divided by k. So as you can see here, the gravitational wave spectrum follows k to the second power in these units of omega divided by k until a time which is proportional to 1 divided by wave number, and then it becomes flat, which is what we were observing in these simulations. So with this idea in mind, in this recent paper, we have developed an analytical model in which we're assuming that the actual gravitational wave dynamics are actually much lower than those from the magnetic field evolution, since these are characterized by 1 divided by k, and the dynamical evolution of the turbulence, in this case of magnetic fields, is characterized by the Alpen speed, which by causality is always smaller than the speed of light. And therefore, at wave numbers that are larger than this fraction of the characteristic scale, this will be true. The assumption that the gravitational wave dynamics are smaller, are much slower than those from magnetic field. This allowed us to derive this model that you can find in this paper. And after we performed numerical simulations in order to validate this model, we observed that actually we find this k to the third power spectrum at the smallest wave numbers that then goes into this linear k, which was corresponding to the flat spectrum that I showed before. And then it would follow at the k to the minus 8 thirds that was also observed for Kolmogorov turbulence. So these blue and red dots are obtained from numerical simulations, and the black dots are compared with this analytical model that we have obtained. And for this analytical model, we are using some results from the numerical simulations in order to study what is the effective duration of the turbulence. So not going to go into much detail, but you can find the details here, or you can ask me later on if you're interested. But with this model and the validation from the numerical simulations, we were able to study what is the final spectral shape that we expect for this type of signals, and to actually give what is the effective duration in relation to the actual magnetic field dynamical evolution, which is governed by this Alpen speed. So we use this model to give some constraints on primordial magnetic fields by comparing to the results from pulsar timing array. And again, in this, I'm gonna just skip this part, since I just wanted to show that we have been using this model for some prediction of what is the characteristic strength of magnetic fields at their coherence length scale, and then we can compare these with actual astrophysical constraints that have been observed for the larger scales in our universe. And in future, we are planning to also apply this for to the constraints that we can actually put on these primordial magnetic fields with LISA, or with a potential observation and non-observation of these signals with LISA. So up to this moment, the simulations that I was showing are assuming that the magnetic field is already present at the initial time. And this is a bit unrealistic, since we are neglecting the initial phase of growth of the magnetic field, which can actually lead to the enhancement of gravitational waves, as I will be showing in a moment. And some previous simulations that we did regarding to this was in order to model in an ad hoc way the production of magnetic fields, we introduced a random electromotive force in the induction equation, which was also following Gaussian noise and with some specific helicity. And therefore, we were studying this same system of equations, but instead of assuming that the magnetic field was initially present, we were adding this electromotive force for a short duration of around 10% 1 Hubble time. So when we were doing this, we were finding that the magnetic field was was then being generated and was following a turbulence spectrum. And then we also studied what was the production of gravitational waves. So let me just go into the results. So here in brown is the results that I was showing one moment ago. For the case where we have the magnetic field already present, and when we are including this initial growth phase, then we see an enhancement and some modifications on the spectral shape for different values of the helicity. So this is for a non-helical and for a fully helical field, which is mostly affecting the inertial range of the gravitational wave spectrum. Finally, this is compared to acoustic turbulence, and in the end, what we want to have is a global picture where we have the realistic scenarios of magnetic field production, and therefore also the relative amplitudes of the acoustic turbulence with the vertical turbulence to have the final gravitational wave signal. But in this case, we are studying in particular what would be the gravitational wave signal and the effect of having an initial magnetic field actually produced in the final spectral shape of gravitational waves. So as you can see, it is pretty relevant to have the realistic magnetogenesis scenario on the final spectral shape compared to the one where we are ignoring that, and that is something that we are currently working on. And we are studying different magnetogenesis scenarios and the production of gravitational waves by trying to incorporate such early dynamics of the magnetic field into the final resulting gravitational wave spectrum. So this is very briefly, I have time. I will very briefly comment on the production of polarization in these signals. So if we have, for example, helical magnetic fields, so I was showing one of the parameters is this fractional helicity, and we can produce helical magnetic fields in many beyond standard model, in standard model extensions, which are also required for, as Mark Hahnemann was explaining, for baryogenesis, for the production of baryons. If we have such symmetry breaking, we might produce helical magnetic fields. And at the same time, these helical magnetic fields would induce then circularly polarized gravitational waves. So for that purpose, we have also been studying in these numerical simulations what would be the circular polarization, which is given by the fraction of the antisymmetric spectrum divided by the energy density spectrum, which is what I was, the spectrum that I was showing before. So from these numerical simulations, we can observe that the polarization spectrum, in this case, it's slightly different for the case where we're assuming that the magnetic field is initially present. And this can actually be reproduced with some analytical model that was previously derived in 2005 by Tina Kagnesvili and others, and that we have slightly improved in this recent paper. But in the case where we have an initially driven field, then these early analytical models fail in predict the final spectral shape, and we can give those spectral shapes with the numerical simulations for the polarization of gravitational waves. Again, this then highly depends on the specific magnetogenesis scenario that we consider. So if we consider these signals, it might be possible to detect polarization with LISAs. It has been proposed by the dipole response function, which can be induced in an isotropic gravitational wave background due to the proper motion of the solar system. But however, we have observed in this paper where we studied these type of signals that this is in general not enough to be able to probe the polarization of such of the polarized gravitational wave background produced by MHD turbulence. However, if we have LISA and some other space-based gravitational detectors, for example, TAIGI, then we might be able to actually observe such signals with signals to noise ratio above 10. And we have slightly different expectations for kinetically dominated turbulence than for magnetically dominated turbulence. So this could be, for example, one way to disentangle the two signals if we're actually able to observe such polarization. So with this, I conclude. I think I'm a bit above time, so maybe I can just keep mentioning the conclusions. And thank you very much for your attention. Let me know if you have any questions.
All right, thank you a lot, Alberto. And I open the floor for questions. So please raise your hands as usual, or drop your question in the chat. Mark, go ahead.
Yes, thanks for the talk, Alberto. And so just picking up on something you said just now, which is the difference between the signal from kinetic turbulence and the signal when you have magnetic fields involved. And just the sort of the next to last slide you showed, just by eye, they look rather similar. And I guess I'm actually interested in the unpolarized case as well. So is there what are the prospects for being able to measure the magnetic field, for example?
So yeah, I mean, as you're saying, there are not actually many differences. It's mostly in the lower frequencies. So in the higher scales that we have in the case of kinetic turbulence, we have slightly an increase in the polarization at the smaller frequencies with respect to the magnetic turbulence case. And yeah, I mean, since this is directly the antisymmetric spectrum of gravitational waves, so in this case, this is completely proportional to the fractional helicity of the magnetic fields, right? So therefore, we have as we decrease the helicity of the magnetic fields or the velocity fields, therefore this antisymmetric spectrum decreases actually. So we have higher expectancies of observing such a signal if this is fully polarized, where we have a fully polarized magnetic field, fully helical magnetic field, therefore fully polarized gravitational wave signal.
So, but do you have a comparison of the not the difference, but the sum, so that where
of the sum of the two of these?
I mean, the signal from both. If you weren't interested in polarization, what is the total power? Is there a difference between turbulence without a magnetic field and turbulence with a magnetic field?
Yeah, I mean, for example, in this first case, this could be this is called kinetic turbulence would be without the presence of a magnetic field. So in this case, we haven't studied what would be like the contribution from both sources, because for that we could actually need to study what would be the relative amplitudes of the velocity of magnetic fields. So here we have studied both separately. But yeah, I mean, in future we could actually study what is the production of the magnetic fields from the velocity fields in a realistic phase transition, and therefore having like the contribution from both sources directly.
Okay, thank you.
That's that. Yeah, thank you.
All right, is there any other question for Alberto? If not, I suggest we thank Alberto and Mark again, and we can close our session here. I would like to remind you that there are different pre-recorded talks that you can access through the LISA Symposium website. And if you're interested, please just go there and have a look at that. There are a few of them related to cosmology that might be of interest for you. Okay, so let's close it here. I wish you all a good continuation of the LISA Symposium, and I think other sessions are still on, and in any case, tomorrow we will start with parallel sessions. With plenary sessions. Have a good rest of the day, everybody. Bye.
Thank you, Nicola. Bye, everybody.
Thank you.
Thank
Bye.
you.
Thank you. Bye-bye, everybody. All very interesting.
Bye.